processing data for ML. Let's go ahead and dive into this AWS Academy created presentation that I'm going to annotate here with my own thoughts. Let's go ahead and talk first about an introduction, and we're going to get into labels, features, samples, the lifecycle of ML, also key considerations and tasks. We'll talk about pre-processing, feature engineering, data transformation, also the ML services and how they're used for AWS in terms of the AWS ML lifecycle. We'll talk about SageMaker. We'll define GenAI. We'll talk about Code Whisper inside of Jupyter Notebook, and we'll talk as well about some use cases. So this is a pretty big talk here, and I'm going to go through it pretty quickly. So let's first start off with concepts, processing data for ML. So ML, if you think about it in terms of a comparison to traditional analytics here, with traditional methods, developers or data scientists are going to write programming logic to represent rules, and these are going to be applied to a particular outcome. But with machine learning, the rules are not hard-coded, and these practitioners are going to build a mathematical function that finds patterns in historical data and uses those patterns to predict the outcome. Some of the algorithms as well are important to consider. So machine learning model is a mathematical model that is going to map the input to a set of predicted outcomes using an algorithm. And when you start going through and building this model, the precise definition isn't known yet. You're going to start with a clean data set, and it's going to be prepared for the machine learning model as well. And then an algorithm is going to fit the data and the type of problem you're trying to solve. And these algorithms are standard methods that define the rules of the model. And you can think of them like a recipe, and the model's maybe the cake. And you can use the algorithm with your ingredients, which would be the data, and you can evaluate what it will produce. So what does it actually taste like? And then you can adjust it. So it's an iterative process, and you can use the same ingredients in a different recipe, and you can get a slightly different cake or a different dessert. So that's a nice analogy to really think about when you're considering what machine learning is. And the model is a combination of the trained data and the algorithm that you use. So first, let's define the general types of machine learning models. This is a very important concept to drill down on, and there are different processing steps for each of them, but there are some similarities as well. Like, for example, using a data set and an algorithm to train a model. First up, we have supervised learning, and this is when a model uses known inputs and outputs to generalize for the future. And an example would be something like, if you wanted to identify a fraudulent transaction, is this fraud, yes or no? And then you would categorize those objects into a group. For example, is this an image, a dog, a cat, or a bear? So, again, for supervised machine learning, linear regression, right, doing a numerical prediction is pretty common, or doing a logistic regression, which is breaking things into a category and saying, again, cat or dog. That's a very common supervised machine learning because you know what the labels are, and you can do a prediction based on historical data. Now, in terms of unsupervised machine learning, one of the ways I like to phrase this is that it's a discovery process. So the model doesn't know inputs or outputs. So you're really doing a discovery on data to find hidden patterns. And a good example of this would be clustering. Now, with reinforcement learning, the model is going to interact with the environment, and it's going to learn through trial and error and take actions that will maximize the reward. You can see this with like very simple self-driving car examples. Those are reinforcement learning. For example, if maybe a model car went through a track and it did something incorrectly, you would penalize it. When it does something correctly, you would reward it. Now, in terms of the subcategories of AI, it's important to break into some of these as well. So first, we have a neural network, and this is based on a collection of connected units or nodes that loosely model the neurons in a biological brain. And with deep learning, a model can recognize patterns that are several magnitudes more complex than other models. And deep learning is a machine that can learn to play, for example, chess or other kinds of games, StarCraft, And in terms of deep learning, it can solve more complex problems, but requires a lot of compute power. And this is what makes it different. And the idea of deep learning and neural networks have been around for quite some time, in fact, decades and decades. But really, the compute power was the thing that was missing, and also the style of compute, right? In terms of having very dense computational architectures like a GPU or even these newer chips that are designed for AI. And then generative AI is a type of AI that can create new content or ideas, including conversation stories, etc. And these are powered by large language models that are pre-trained on a lot of data, and they're commonly referred to as foundation models. And the difference between a traditional model is that the traditional models are usually a task focus. So they're going to solve one particular problem, but a single foundational model can be used for lots of different tasks like text generation, summarization, and you don't have to train it necessarily again. And so some of the things that people are using them for: chatbots, assistants, personalization, content moderation. If we think about the evolution of machine learning for practical use, it can go back even to the 50s, where the experts were thinking about intelligent systems, but the computers weren't fast enough. And then in the 70s, there's these expert systems. In fact, when I was in college, I did a little bit of work with expert systems. And then these expert systems gave people an understanding of what computer-based intelligence actually was. But then the neural network is what really started to take off. And this was around maybe 98. And things started to convert to machine learning. So some of this is very new in terms of the new approaches with deep learning. And so in order to do this, there's really a necessary amount of large computational power and large data. And one of the ways that you can think about this is that right around 2007, that combination really gelled together. And now with the availability of GPUs, machine learning has really gone into a modern era now. And with 2017, some of the breakthroughs, for example, the transformer architecture that Google was first leading with, has now moved over to Hugging Face. And this is really the foundation for new generative AI. So some of the ML data concepts, we can take a look here at a label or target. This would be the outcome. And it's also known as a class, a dependent variable, or a response. So this is what you're trying to predict in English. A feature is an attribute or independent variable, and this is known as the predictor. And these are details that describe the target. And then a sample is an occurrence of a target and its feature. So this would be, some rows, for example, in a column, and all the columns in a spreadsheet. So a sample would be, basically, multiple observations inside of a spreadsheet. Now, in terms of the key takeaways here, a model is a function that uses an algorithm and a trained data set to predict outcomes. And machine learning can be divided into supervised, unsupervised, and reinforcement learning. And deep learning is a subcategory of machine learning where the models are developed using neural networks, and these models can recognize patterns that are much more complex than traditional algorithms. So let's talk about the ML lifecycle here next. And an ML application is a specific use case of a data pipeline, and it will involve several things: ingestion, storage, processing, analysis, and visualization. And you're going to see in this life cycle that it's very iterative as well. And one of the things to think about is that the results are going to feed back into determining whether the business goal is met. So if you build a machine learning model and it doesn't actually solve a problem, then it doesn't matter how good it was, because you're trying to ultimately solve a business problem with production machine learning. And the data phase can be segmented into two steps: the collection data phase and also the preparation data phase. And the preparation data set is also split into two closely related tasks, which are pre-processing and feature engineering. So if we think about the common roles of a data scientist when you're solving a particular problem, the data scientist can be identifying the data. Maybe the data engineer is a primary owner of collecting the data and making the data pipeline work. And then the data scientist is going to process that data and develop the model and then hand it off to the ops team to monitor it into production. Now, that's a very big organization. At a smaller organization, it's possible that one person is doing the entire thing. But if there's an architect, the architect could also design the infrastructure and workflow. And so a data engineer may not typically do model development or deployment, but it really depends on the size of the organization. So I think one thing to be aware of is that these are very fluid roles. A machine learning engineer, ML ops engineer, data scientist. And in some organizations, they're all separate. In some organizations, it's all the same person. And so the key takeaways are that an ML lifecycle would take a business problem and frame it as machine learning. The data engineer would work with the data scientist to collect the relevant data and prepare it for modeling through pre-processing and feature engineering. And then a data scientist is going to go through and make sure that the model is going to do what you think it's going to do. And then the operations team, again, maybe the ML ops team, is going to deploy it into production and make sure that the monitoring is in place. So let's talk next here about framing the problem. And so it's important to work backwards from the goal and then figure out how machine learning is going to help you solve the problem. For example, what is the real problem we're solving? What pain is it causing? When does this problem need to be resolved? It really doesn't matter how good your machine learning system is and how well the model is at predicting things if you're predicting the wrong thing. And if we look at a problem statement, it's a concise statement that summarizes the answers to a question. So, for example, in a case of a company, they don't know why there's increased fraud, and they want to know what kind of insurance claims represent the most fraud, and then where's that fraud occurring. And so a machine learning solution could help them identify predictions so that they could adjust accordingly based on what they find. So framing the problem is really important because you can use the domain expertise. So this is the business expert that understands the business, and then the data scientist who understands the data science to determine if machine learning can address a business goal. And these steps are really important to think about. And some of the things that we can consider, for example, what is going to be observed, the feature, what's going to be predicted, the label of the target. You want to establish observable, quantifiable metrics. You want to make sure you have a strategy for data sourcing. And now you could also say you also want to have a strategy for ethical data sourcing. A lot of people just talk about data sourcing, but for example, if we stole the data from somebody else and we don't have their permission for it and we're basically infringing on their intellectual property rights, that is a situation where you definitely want to be aware of what it is you're doing. And also, do you want to evaluate whether machine learning is the correct approach? And then you want to start with a very simple, like the simplest model you can and iterate. You don't want to start with like a very complex, maybe ensemble model. And an ensemble model would be lots of different machine learning models together. Maybe you start with linear regression, right? You start with something simple and see if it is good enough. So if you think about machine learning and whether it's the best approach, a few different things you can think about is, you can almost have a flow chart. You can say, can the business rules be hard coded? Yes. Are the number of variables limited? Yes. Can statistical modeling solve the problem? Yes. Can this method respond quickly enough? Yes. So you basically can say, okay, maybe that's an analytic solution. And then if it's no, what you could do is you could say, maybe we can consider a machine learning solution. So then you have to go, do we have enough data? And is it high quality? And can a machine learning model, provide the level of accuracy, latency, and transparency? Well, and then another one is, does your organization know how to do this? And then what's the actual cost? So even if you do decide that you're going to build a machine learning solution, it's important to actually drill down into what that actually means. So in terms of problem framing, you can think about, for example, maybe a data scientist is working with a domain expert for car insurance claims, and they have a database, and that domain expert has information that can identify fraudulent claims, and they find there's maybe 1,000 claims from the previous 12 months, and they could figure out, could we actually predict which ones would be fraudulent. So some of the key takeaways would be that you want to work backwards from the business goal to ensure the product is going to meet the needs. You want data scientists and domain experts to work together to frame the problem. And this can really be a challenge, right? Because if the business is actually asking for one thing and the data scientist is asking for another thing, you could create the perfect solution that doesn't work because it doesn't solve the business problem. So machine learning isn't always the correct answer, and that's important to be aware of. Okay, let's get into collecting data here next. If we think about collecting data in the machine learning lifecycle, you're going to have to get it from the source and then move it to a location where the data scientist can prepare it for machine learning. And this can be a very challenging part of the problem. And this is where the data pipeline comes in. And then a common ingestion pipeline for machine learning would go through an extract, load, transform, or do an ETL operation, put it into a data lake, do some transformations. And then some of the things to consider would be there's going to be discovery cycles. So it's not like you just put it in there once and you're done, you walk away. That you're going to have something that's flexible enough that you can do discovery, ingestion, visualization, processing, and the person that's going to perform that data engineering is going to be responsible for getting the data into the pipeline and loading it into the data lake. And so there could be different roles that are involved. It could be a data engineer, it could be a data scientist, or again, it could be the same person. Now, in terms of the key steps in collecting data to be used in machine learning, this would be ingesting, preparing data, ingesting by batch, stream, and some of the things to consider would be, applying labels to supervised models as well. In terms of protecting data veracity, there's another thing to consider is that data scientists might perform the majority of the cleaning tasks as part of the preparation for the correct machine learning algorithm. So for example, let's say that you're clustering your data. Well, one of the things that you may need to do to prepare is that you have to do some kind of scaling so that all of the columns that you're working with are relative, so you don't have one column that's skewing the results in a particular direction, because the way that scaling works is that, the way that clustering works is that in a multidimensional space, you're finding out, what clusters are actually grouped together. And in order to do that, you need to have a uniform scaling. And so these kinds of things can take work. They can take data engineering resources. They can take computational resources. And so that's why there's a group effort involved. Now, another thing to consider would be that a data engineer isn't going to be responsible for deciding how to, let's say, split up a data set for training and test data. There's common approaches like 80-20 split or, 70-30 split. The data scientist is going to, in some cases, be doing this partitioning so that they can figure out what the quantity is. And the volume and quantity of the available data is really important when you're trying to figure out how to make one of these solutions. And another thing to consider is that, the rule of thumb is 70 to 80% of the collected data is used to train the model, and the rest is going to be used to test and tune the model. So the idea here is that you don't want to use all of your data, because you also have to validate that the thing that you built is going to work on data it hasn't seen yet. And so this is an important distinction when you're figuring out your production system. Now, some of the key takeaways here are that in order to collect the data, it's going to be similar to ELT ingestion. A big key aspect of this is to ensure that there are data sources that can provide enough high quality data to account for training and testing. And then the labeling of the data is also going to be a task that's going to happen during the data collection. Okay, let's get into labeling the data here a little bit. So in machine learning, the data labeling is a process of identifying targets in raw data like images, tabular data, text writing, videos. The process is going to involve one or more meaningful and informative labels so that the machine learning system can learn from it. So the classic example is, there's a photo, is it a cat or is it a dog? Or in an audio recording, what words are uttered, or in terms of an x-ray, does it have a tumor or not a tumor? And in terms of data labeling, this is going to start by asking the human to make a judgment about a given piece of unlabeled data For example, does this photo contain a dog? So then the tagging can be a really rough, simple yes or no. Now, if we think about tabular data labeling, that's one of the easier ones to really visualize, is that a labeling task would identify which samples in the ingested data set were fraudulent. For example, is it fraud? Now, if we look at other kinds of labeling, we have things like computer vision. This would be, objects or categories within an image, like bounding boxes. We have natural language processing, doing things like sentiment analysis or recognizing named entities. With audio processing, it could be, interpreting sounds like speech, wildlife, or even noises like machine noises. Now, if we think through some of the systems of AWS, we have AWS SageMaker Ground Truth, and this is a tool that you can use to organize and complete labeling tasks. So you upload a bunch of unlabeled data to S3, and then you set up a labeling job, and then inside you can have people be the labeling workforce and provide instructions and a UI to make it easy to label. So this is a very significant part of a machine learning problem. One of the messy things is that how do you actually get the data that you have so that it's in a state that you can do the machine learning. So this kind of a system is actually a fairly common system in large-scale machine learning models and at a larger organizational level. Okay, so some of the key takeaways here is that labeling is an act of using labels to target. In training data, labeling can be done on images and video for computer vision, on text for NLP, and on audio to categorize sounds. The tools include things like SageMaker Ground Truth that you can actually use to orchestrate this labeling process. Okay, so pre-processing data here. Let's go ahead and talk about the steps of data pre-processing, feature engineering, and model development. They're all going to be intertwined. They're going to be iterative. And so data pre-processing puts the data into a correct shape and quality for training. So that's really the goal here, is like, can we get the data into a shape and a level of quality that we can actually use it? And with machine learning data processing, it's mostly the data scientist role to work to prepare and wrangle that data. So there could be some software engineering skills that are required in order to do that. And these could involve things like, pre-processing activities. These could involve things like, normalization, scaling the data, and visualizing the data as well. Doing things like exploratory data analysis with visualization tools, like, what is it I'm even looking at? And again, it's not going to be a static process. It's going to be a very dynamic and iterative process. In terms of pre-processing strategies, the data scientist is going to apply those strategies based on the data sets and intended use cases. And these could include statistical modeling techniques initially. So maybe you do a histogram to see, what's going on, or skew, etc. But these individual strategies are actually listed according to looking at unbiased data. And so to produce accurate predictions, it's important that the data scientist identify and migrate bias in the data. So a good example is if the goal is to predict, let's say, customers, but the data set includes a large percentage of samples from only one country, and you're trying to do a global prediction, you're going to have a biased set. And data wrangling tools can actually improve the approach of some of these strategies, and the pre-processing is then going to be closely tied to feature engineering. So feature engineering is something that we'll get into in a little bit, but basically you're building ways to building features that can be used to make more accurate predictions. So if we think about pre-processing for fraud detection, maybe you would convert a Y or no in the is this fraud field to a numeric equivalent. So in general, machine learning likes numeric data. So if you have something that's text, most likely it will be converted to a numerical format so the machine learning model can work. Even though you may not be seeing it, that's what's going to happen beneath the hood. Now, in terms of data exploration, another thing to consider would be that you might even start off with things like Excel, maybe use some Python, PySpark, etc. But initially, you need to actually get a feel for finding patterns, looking at the relevant discovery type algorithms so that you understand how to go to the next step. So the key takeaways here are that the goal of data preprocessing is to start preparing the data for training, and typically a data scientist would be doing the preprocessing. Okay, let's get into feature engineering, and we'll talk about what that is. So feature engineering is a process to select and transform the features or the variables that are going to improve the selected algorithm so that you can use it. So feature engineering is also a way to improve the accuracy and the performance of the model. The data scientist will need to apply the domain knowledge and statistical modeling to perform the feature engineering. So you need to have both to do this correctly. So like if you're doing something with the basketball, right? You did an NBA feature engineering project, you would have to know about some of the unique things that happen in a basketball game, plus you have to know the statistical features. All right, if we think about feature creation and transformation, one feature creation technique is called binning, and with binning, you would convert the continuous data into groups called bins, and then by grouping these items, you can provide a fixed number of values to work with, which might be easier for an algorithm to work with. We also have dimensionality, which is a classic problem in feature engineering, and this means like how many features does your data set have? Or an easier way to say this would be how many columns does it have? If you have very high dimensional data, they call that the curse of dimensionality. And so with high dimension data, the data is going to be in some cases too large to work with, and so you have to somehow manipulate that data so you can work with it. And feature selection would be removing features that don't appear to have high value in predicting, and a domain expert could just drop a bunch of these. Like for example, we have certain things, they don't seem to have any signal, and so let's go ahead and just take them out of the data set. A few things that are takeaways here are that the feature engineering step is about using the existing features and improving them, but it could involve creating and transforming new values or new features. For example, if it's a basketball new feature that you're creating, you could say, did the winning season or losing season, right? Like you're creating a new feature based on data that already exists. Okay, let's talk about developing a model here next. The model development process is going to involve building, training, tuning, evaluating, and model building is going to include the algorithm and supported code all at the same time. And so the model is going to learn through a repetitive training process by finding patterns, making predictions on those patterns, and then evaluating the quality of the predictions. And the time and resources that are required to train the model are related to the type of model that you're running and the data set you're using to train the model. And an example would be a deep learning model could require a very high level training versus, let's say, a regular supervised machine learning model that does binary prediction. So some of the things to consider in the real world is that you have to monitor the errors that happen in a training process, right? It's a computer software problem really at its heart. And so you're going to have to figure out things like, what are the parameters of the values that you could use to estimate from the data? What kind of hyperparameters are you going to use? And hyperparameters control the model learning process. So a really good example of a hyperparameter would be how many clusters to pick in k-means clustering, right? Do I want to try to do 3 clusters or 4 clusters? That would be hyperparameter selection. And in terms of what a data scientist would do is they're going to iterate on training and tuning the model until the error rates are going to be accurate enough for the business problem. So another really big one that trips up many people is accuracy metrics. And accuracy metrics and methods for tuning the model are a lot more complex than you really can get into in a brief talk. But basically, accuracy is the base metric that's going to be used to evaluate a model, and it's the measure of the number of correct predictions when compared to all the other predictions made. And we can dive into a few of these in a little bit, but basically some of the things to consider would be that the process of building, training, and tuning the model is going to be extremely resource intensive, and model development is iterative, and training activities often work with big data frameworks like Spark, for example, could be one example. But just because it's big doesn't always mean it's better. Sometimes really simple models actually are a lot better. But let's go ahead and talk about wrapping this section up. Model development is at the heart of machine learning. A model is trained and tuned until it reaches accuracy. The test data is used to validate it. So again, you hold out that data so that you're not training it on data you've already seen. You can actually test it on really some fresh sample to validate this. Okay, let's talk about deploying model, which is a big part of ML ops. Is, hey, does it actually work in production? So standard debugging and logging of an application are part of monitoring the deployed model, and you can capture normal application metrics and actually do things like slow queries, high latency, etc. But the model output in production is critical to make sure that you're getting the expected level of accuracy within a production data set. So you're going to have to monitor it like a real system, like an HTTP service or a database service. Now, in terms of looking at things in production, one of the things that the model is going to take in is individual samples and provide an output. And you could even compare this to the training environment where the model is going to churn through a bunch of transactions in parallel. And it's also important to know that you want to make sure that it performs as expected in production, but also at a reasonable cost. And so there are choices that you're going to need to make. For example, can you do a batch job? Maybe that's good enough. And you can do that in a very cost-effective way. Or there's real-time inference, which in some cases could be more expensive, but maybe you get low latency, and so you're okay with it. And then finally, MLOps is a approach to maintaining the model pipeline. So it really builds on top of DevOps. And the idea here is that you treat the model just like you would treat the rest of the software stack, which is you're continuously deploying, continuously testing, tuning things, maybe redeploying the model when it reaches a certain metric. So it's really builds on top of the CI/CD pipeline. So people that have DevOps skills are actually a very good fit for getting involved with MLOps because it's just an extension of what's already happening with DevOps. One of the things I like to say is you cannot have MLOps if you don't have DevOps. If you don't have DevOps, you have to first start there. So some of the key takeaways here would be that when a model is deployed into production, the infrastructure is going to have different characteristics than the training environment, and the code and infrastructure that are related to the production model are referred to as inference. And there's a large number of roles in different environments that could be part of a automated deployment strategy. And finally, MLOps is really a best practice that builds on top of DevOps, but with models. Okay, ML infrastructure on AWS. Let's talk about this next. So some of the things to consider would be, what are the different services you want to use? Do you want to use workflow services like SageMaker or AWS Batch, frameworks like TensorFlow, PyTorch, also compute, network, and storage? Like, what are these compute systems? Let's first get into compute and network services. We have things like Amazon Elastic Compute Cloud or EC2, and we have ones that are targeted towards doing ML, like P3, P4 are GPU based, and the G4 and INF1 instances are also well suited for doing deployment. And with elastic inference, you can actually attach a low-cost GPU, and you can reduce the cost of running deep learning inference. There's also Elastic Fabric Adapter, which is a network interface that has low latency connection between instances in a clustered configuration, and this can help models train faster. So there's some very unique and specialized hardware for training and inference. Inference just means prediction on the AWS cloud. Now, in terms of storage, this is another very interesting one, is that we've got, S3, and this could be where you're doing things like object storage, block storage with EBS. EFS would be maybe the ability to provide easy access to models and data sets because it's a managed network file system. And then we've got Amazon FSx, which is file system storage for Lustre. Okay, in terms of workflow services to simplify creating machine learning models, we've got things like the AMIs that are pre-installed. And I think this is kind of a no-brainer for certain things. Like, why would you install this software? Like GPU drivers are notoriously difficult to install, and an AMI simplifies that. We also have deep learning containers, even better, right? Like you have a pre-installed deep learning framework. And then we have things like fully managed container orchestration, like Amazon ECS or Amazon EKS. We also have workflow services that are pretty interesting, like Amazon EMR. This would be big data service. Amazon Batch, fully scheduled managed service that can do ML jobs. So again, if you want to do like one of the most cost-effective batch-based inferences, you could do AWS Batch. It's pretty tough to beat. We also have open source cluster management tools like AWS Parallel Cluster. So the big takeaways here is that AWS ML infrastructure is grouped into three layers: compute, networking, and storage. And at the bottom, and the workflow services, if you think about these things, they're going to involve lots of different components and even overlap. And so it's up to you to figure out the best tool. Let's talk about SageMaker here as well. So SageMaker has even additional tools. There's Studio, which is a web-based virtual interface. There's SageMaker Data Wrangler, which does data prep and feature. There's SageMaker Processing, which is simplified experience for ML processing. And then there's Canvas, which is like kind of a point-and-click system. So in terms of SageMaker Studio, the thing to consider would be that it's a IDE for ML, and it now even includes a cloud-based editor, which is a really cool feature. And the Data Wrangler is going to allow you to maybe automatically generate data quality insights. And then if you're processing big data using things like Jupyter Notebook, you can use SageMaker Studio Notebooks. And then for Amazon SageMaker Processing, it's a tool that you can use to analyze data and evaluate models. So the other thing to consider as well is that SageMaker comes with a bunch of algorithmic choices and pre-built solutions. Now, if we talk about training and deploying a model with SageMaker, a few things to consider would be the training job includes things like the URL of the S3 bucket, the compute resources, also the URL of the bucket you want to store the output, and then maybe Amazon Elastic Container Registry or ECR. And then after you create the training job, SageMaker is going to launch the ML compute instance and use that training code and training dataset to train the model. So SageMaker Canvas is another one to consider, and this is going to just really be like a point-and-click way to build a model and make predictions. So you need to really know not a lot of coding, if any, to use a tool like SageMaker Canvas. So some of the key takeaways here are that SageMaker is a managed service with tools and features that work across the ML lifecycle. SageMaker Studio provides an integrated IDE. SageMaker Hosting will let you do real-time inference or batch transform. And then Canvas is really for non-coders to do ML. Now, there also is a pretty cool feature, which is Amazon Code Whisper. And this is a code-generated coding companion. And this can do whole line functions, and it works with a lot of different services on AWS, including some of the SageMaker components as well. And so if we think about how it works, it uses generative AI. It can create new content and ideas using the chat system that comes with it, and it's a subset of large language models that are trained on trillions of words across many natural language tasks. They can do things like have some understanding of learning, generating text, etc. And then with traditional ML models, you're going to have really a specificity with it, but with large language models, they can work on a lot of different things. So if we think about Code Whisper, a few things to be aware of are that the individual tier is free, and so you can just sign up with an AWS Builder account. The professional tier does things like gives you more admin privileges, which is very helpful because you have the ability potentially to, limit some of the functionality or control it for data governance purposes. Other GenAI services as well include Bedrock, which means that you can talk to lots of different foundational models through a single API. We have Amazon SageMaker Jumpstart, which lets you have a hub with built-in algorithms and pre-built ML solutions. We also have Inferentia, which is a custom ML chip that gives you high-performance inference. And if we really think about some of the takeaways for Code Whisper, is that it can be a very productive tool to make you develop code faster and more secure. Now let's talk about AI and ML services for AWS here. Some of the ones to consider would be, we have recognition, which can do detection of faces, text, logo. We have forecast, which is predicting time series data. We have Amazon Comprehend, which is deriving insights and connections from NLP. We have Transcribe, which is speech to text. We have Amazon Poly, which is text into lifelike speech. And we have Amazon Translate. So these have been around for quite some time, but they're all still pretty useful. We also have workflow that we could talk about. So let's say that we're going to use Comprehend and we wanted to do a pipeline. We could have a list of entities that we discover, like people, places, locations. We could look at key phrases. We could look at the dominant sentiment of a document. So these are specialized models. These are not foundation models. These are specialized models for NLP. So some of the key takeaways are that AWS does have purpose-built solutions for these use cases like NLP, image recognition, time series, and you can just reach them via an API. So it's a big lot of content that we covered here. Let's go ahead and wrap it up. So we talked about machine learning, ML lifecycle, how data engineers and data scientists collect and process data for ML models. And then we talked about the different phases of the ML lifecycle. We talked about framing the ML problem, collecting, pre-processing, feature engineering, model development, model deployment. We also looked at AWS infrastructure services. And then finally, we wrapped it up with AI and ML services you can use to solve common use cases without a lot of machine learning knowledge.